Imagine hitting enter on just like a single line of code, and instantly 100,000 users lose internet access.
Oh, yeah, that is the ultimate nightmare scenario.
Right, because in the world of enterprise networking, one bad command doesn't just mean you failed a test. It means you take down companies, you halt communication, you basically stop the flow of data across the globe.
It is a terrifying amount of power, honestly. And it's exactly why network engineering isn't just about, plugging in cables. It is about understanding the delicate living architecture of how information actually travels.
Which brings us to our mission today for you, our listener. We have a huge stack of source materials in front of us, specifically a set of highly technical practice exam questions and Junos documentation.
Yeah, and we are not just going to memorize definitions today.
No, definitely not. We are going to master the key technical concepts and assessment criteria for the JN0-106 exam. We're going to figure out how these network systems actually breathe, and more importantly, how you keep them from suffocating.
To ground us in what we are actually looking at, the JN0-106 is an associate level certification, the JNCIA-Junos.
Right.
If you were sitting in the exam room, you'd have 90 minutes to tackle 65 multiple-choice questions. Those are a mix of single and multiple response, and they're delivered in English. It is basically the foundational gateway into routing and switching.
So here are our rules of engagement for today's deep dive. We're going to look at 10 specific practice questions from our source stack. And I am going to read the full text of every single question, along with all 4 options, so A, B, C, and D.
All of them.
All of them. But instead of just giving you the answer key, we're going to methodically break down the hidden mechanisms behind every single option. We want you to understand exactly why an answer is right and exactly why the distractors are dead wrong.
Because, the test designers are incredibly smart. The wrong answers usually sound highly technical and completely plausible if you only have a surface-level understanding.
Exactly. So let's just start with the most fundamental rule of networking, which is how to save your own skin before you even begin typing commands.
Always a good place to start.
Yeah. So, question 1. What is the primary purpose of a rescue configuration on a Junos device? The options are A, it automatically restores the device to factory default settings upon a power failure.
Classic distractor.
Right. Option B, it serves as the initial boot file when the operating system is corrupted. Option C, it stores temporary changes made by multiple administrators before a final application. And option D, it provides a known working state that can be easily loaded if a new configuration causes network isolation.
So if you're sitting in the exam room, option A is designed specifically to trick you, because rescue sounds like starting over.
Yeah, like an emergency reset.
Exactly. But think about the mechanical reality of a factory default. A factory default wipes every single piece of routing logic, every password, every IP address.
Oh, wow.
Yeah. So if a router is sitting in a data center 3,000 miles away and you wipe it to factory default, it is completely inaccessible. You haven't rescued it. You've bricked it until someone actually drives out there with a physical console cable.
Okay, that makes sense. So what about option B, the corrupted operating system? If the system is broken, don't I need a rescue file?
You do, but that requires a completely different mechanism, like a USB recovery drive or a snapshot of the OS itself. A configuration file, which is what the prompt is actually asking about, is just a text file of instructions.
Oh, it's just the blueprint.
Right, it's the blueprint. So if the operating system, the actual foundation, is corrupted, having a perfect blueprint doesn't help you. You have to fix the OS first.
Okay, that clears that up. And I know option C is wrong because a temporary workspace is a totally different feature, which I think we'll actually hit on later in this deep dive.
We definitely will.
Which leaves option D, a known working state that saves you from network isolation.
I love this concept. It's exactly like a save point in a video game right before you walk into, a major boss fight.
That is the perfect way to look at it.
You know things might go horribly wrong in the next room, so you hit save. If your new settings accidentally lock you out, you don't have to restart the entire game. You just reload the save point.
It is your ultimate safety net. You build a working configuration, you specifically save it as the rescue, and you just have peace of mind.
Now, once the device is safe from catastrophic failure, it needs a brain to understand the world around it. It basically needs to build a map.
Right.
Which brings us to question 2. Which 2 statements accurately describe the behavior of dynamic routing protocols compared to static routing? The 4 options are A, they require manual updates by an administrator when a physical link fails.
Keep going. Option B, they automatically adapt to network topology changes without human intervention. Option C, they scale much better in large and complex network environments. In option D, they consume absolutely no central processing unit of resources.
Notice the prompt explicitly asks for two statements. So let's look at the mechanical reality here. Option A describes the exact opposite of dynamic protocols.
Because that's static routing.
Yes. Static routing is when a human manually types to get to network X, go out this specific door, and if that door gets boarded up because, I don't know, a backhoe cuts a fiber cable outside, a static route just blindly keeps throwing data at a broken door.
Until a human administrator actually goes in and manually updates it.
Exactly.
Which means option B has to be one of our correct answers. Dynamic protocols automatically adapt to network topology changes without human intervention. But wait, if they are constantly adapting, option D has to be completely false, right?
Oh, absolutely.
Like, how could they consume zero CPU resources?
They definitely can't. In fact, dynamic protocols like OSPF or BGP are essentially massive distributed math problems. The routers are out there constantly sending out hello packets, they're establishing neighbor relationships, and running really complex algorithms.
Like the shortest path first algorithm.
Exactly. To calculate the best routes, that requires significant CPU cycles and memory.
So option D is just a trap for someone who thinks automatic means free.
Basically, yeah.
That leaves us with B and C as the correct pair. Because they adapt automatically, they scale much better in large and complex network environments. I mean, manually typing static routes for a network of 10,000 devices would be a full-time nightmare.
It would be mathematically impossible. The moment you finish typing, the network would have already changed somewhere else.
All right, so we have dynamic protocols figuring out the map, but we need to talk about how we organize the terrain itself. Question 3. In an Internet Protocol version 4 network, which mechanism is used to logically divide a large broadcast domain into smaller, more manageable network segments?
Okay, let's hear the options.
Option A is hardware address filtering. Option B is subnetting. Option C is address resolution. And option D is flow control.
So to really understand this one, we have to look at what a broadcast domain actually is under the hood. When a device sends a broadcast packet, it goes to every single machine on that local network.
Right.
And this isn't just a volume issue. It creates what we call broadcast radiation.
Meaning every single computer CPU actually has to stop what it's doing to process that packet.
Exactly. The network interface card receives the broadcast, interrupts the computer's CPU, and says, hey, is this for us? If you have 5,000 computers in one broadcast domain, every single device is constantly interrupting its CPU to read garbage data it doesn't even need.
It just degrades the entire network's performance.
Tremendously.
Now, looking at the options, option A sounds like a plausible security feature. Hardware address filtering. Couldn't we just filter out the noise?
Well, you can filter specific devices at the switch level using their MSC addresses, sure. But that's a security measure. It doesn't shrink the actual boundary of the broadcast domain itself.
Yeah, okay.
And option C, address resolution, is simply how devices find each other locally. We'll actually cover that mechanism in a bit. And option D, flow control, is a transport layer mechanism to prevent a fast sender from overwhelming a slow receiver.
So the answer is clearly B, subnetting.
Yes. Subnetting uses mathematical boundaries in the IP address to create hard walls. So a broadcast from subnet A physically cannot cross the router into subnet B. It isolates the radiation completely.
Now that we've used subnetting to carve our network into all these tiny specific segments, the router has a new problem. Like, when a packet arrives, how does it choose between a broad route and a highly specific one?
Right, the decision process.
Which brings us to question 4. When using the longest prefix match routing logic, a router receives a packet destined for a specific address that falls within multiple ranges in the routing table. Which route will the router select? The options are A, the route with the lowest administrative distance. Option B, the route associated with the physical interface having the highest bandwidth. Option C, the route with the most specific network mask length. Or option D, the route that was populated into the routing table first.
This question is great because it tests if you understand the actual hierarchy of router decision-making. Option A, administrative distance, is incredibly important, but it solves a completely different problem.
How so?
Administrative distance tells the router which source of information to trust. If OSPF tells the router one path and a static route tells it another, administrative distance acts as a tiebreaker for trustworthiness. But it does not evaluate the destination itself.
Okay, and what about option B, bandwidth? Surely a router wants the fastest path.
Again, bandwidth is a metric used inside a routing protocol to decide the best path to a single, specific destination. But the prompt is asking about a packet matching multiple overlapping destination ranges. The router evaluates the destination before it ever looks at the bandwidth. And option D is honestly just nonsense. The routing table isn't like a deli counter. It doesn't care who took a ticket first.
So the correct answer is C, the route with the most specific network mask length. I always picture this like a mail carrier holding a package.
Oh, that's a good analogy.
Yeah, if that carrier has one broad instruction that says deliver to New York State and a second instruction that says deliver to 123 Main Street, New York, they're obviously going to follow the more specific instruction.
Right.
The longest prefix match is just the router matching the absolute longest string of binary bits to find the exact front door.
That is the perfect way to visualize it. Specificity is the ultimate law in routing logic.
Now, all of this routing logic is great, but the physical reality is that the digital neighborhood of IPv4 is full. I mean, we've basically run out of addresses, which means we have to scale up to the new language, IPv6.
And this is where human readability becomes a massive, massive issue. An IPv4 address is 32 bits long. It's just 4 small blocks of numbers.
Yeah, easy enough to remember.
But an IPv6 address is 128 bits. It's this overwhelmingly long string of hexadecimal characters. If network engineers had to type out the full address every single time, the human error rate would just skyrocket.
Which sets us up perfectly for question 5. Which statement accurately describes a rule for shortening an Internet Protocol version 6 address? Options are A, trailing zeros in any hexadecimal block can be omitted. Option B, multiple blocks of consecutive zeros can be replaced by double colons multiple times. Option C, any single continuous block of numbers can be replaced by a single colon. And option D, leading zeros in any individual hexadecimal block can be omitted.
We have to eliminate the rules that would basically break the underlying math here. Option B is a classic distractor. You can replace consecutive blocks of zeros with a double colon, yes, but you can only do it exactly once per address.
Only once.
Only once. Because if you use double colons multiple times, the router has absolutely no way of knowing how many blocks of zeros belong to the first set versus the second set. It creates mathematical ambiguity, and routers despise ambiguity.
And option C is just totally invalid notation.
Right.
A single colon is simply the separator between the blocks, like a comma in a sentence. You can't just delete numbers and leave a colon.
Exactly.
Which leaves option D is correct. Leading zeros in any individual hexadecimal block can be omitted. But wait, I had to push back here. Why only leading zeros? Why is option A, omitting trailing zeros, such a catastrophic mistake?
Yeah.
I mean, a zero is just a placeholder, right?
Well, it's all about positional value. It's exactly like basic math. Think about a hexadecimal block like the number 0050. If you drop the leading zeros, you get 50. The mathematical value is still 50.
Okay.
But if your block was 5000 and you dropped the trailing zeros, you're left with just 5. You fundamentally changed the actual mathematical destination from 5,000 down to 5.
You'd literally be sending the packet to a completely different part of the internet.
Exactly. You can drop leading zeros because they don't change the magnitude of the value.
That makes total sense. So with these complex IPv6 addresses and dynamic protocols burning up the CPU, how does a router actually handle millions of packets a second without crashing?
That is the magic of modern architecture.
That's question 6. During the processing of network traffic, which type of data is handled exclusively by the packet forwarding engine without interrupting the routing engine?
Let's hear the options.
Option A is routing updates from a neighboring autonomous system. Option B is transit traffic passing through the router to another destination. Option C is echo requests addressed directly to the router interface. And option D is remote terminal traffic establishing a management session.
This question fundamentally tests your understanding of the separation of planes. Junos architecture splits the workload into a control plane and a forwarding plane.
Okay.
The routing engine, the RE, is the control plane. It's the brain. The packet forwarding engine, the PFE, is the forwarding plane. It's the muscle.
So we have to figure out which of these options requires the brain and which only requires the muscle. Yeah. Option A, routing updates, obviously requires the brain because the router has to process new maps.
Right.
Option C, an echo request, like a ping, sent directly to the router itself, means the router is the final destination. The brain has to formulate a reply.
Yes. And option D, establishing a remote management session via SSH, absolutely requires the routing engine to handle cryptographic keys, authentication, user permissions.
So B is correct. Transit traffic passing through the router to another destination. It's essentially brain versus brawn.
Exactly.
The routing engine is the high-level manager sitting in the office upstairs, and the packet forwarding engine is the forklift driver on the warehouse floor. If a box comes in the dock and just needs to be moved out the back door, the forklift driver, the PFE, just moves it.
Yep.
The manager upstairs shouldn't be interrupted thousands of times a second just to approve a box simply passing through.
That separation is exactly why modern routers can forward terabits of data per second. The hardware forwarding table is pre-programmed by the routing engine, so the PFE just looks at the destination, matches it, and blasts it out the interface instantly.
But because that forwarding is happening at such blistering speeds, we have to protect the system from human error.
We really do.
Which leads us to question 7. Which two statements describe the properties of the candidate configuration in a Junos device?
2 statements again.
Yep. A, it is the configuration file currently actively forwarding network traffic. B, it serves as a temporary workspace where configuration changes are constructed. C, it immediately impacts network operations the moment a structural change is typed. D, it must be explicitly applied by the user before the changes take effect on the system.
Once again, we need 2 correct statements. Option A describes the active configuration, so that's out. Option C describes the behavior of many older router operating systems where the moment you type a command, the router immediately executes it. But Junos intentionally avoids that.
Meaning B and D are the correct answers. It serves as a temporary workspace, and it must be explicitly applied. But wait, if the network is literally on fire and I need to fix it right now, isn't having a candidate configuration just going to slow down my emergency fix? Like, why wouldn't I want my commands to apply immediately?
Because immediate application is usually what causes a fire in the first place. Imagine you're typing a complex command to change an interface IP address and your finger just slips. In an immediate execution system, that typo instantly tears down your connection. You are locked out. In Junos, the candidate configuration acts as a buffer. You can make 20 different structural changes across multiple protocols. None of it goes live until you type the word commit. And more importantly, Junos actually runs a background check to ensure your new syntax is logically sound before it lets it go active.
It's exactly like a rough draft of an email. You can type, you can delete, you can write 3 different versions in that draft window. But absolutely nothing happens, nobody reads it, and no damage is done until you explicitly click send.
It is the single most beloved feature among Junos engineers. I mean, it saves careers daily.
Speaking of saving careers, how do we restrict who is even allowed to write those drafts?
Good question.
Question 8. In the Junos operating system, how are user permissions and access levels primarily defined and controlled? Options. A, by assigning specific privilege levels encoded within the password string.
Oh, no.
B, by tying the user account to a physical management port. C, by assigning the user account to a specific login class. D, by requiring secondary authentication through an external server only.
Let's systematically dismantle the wrong answers here. Option A is terrifying from a security perspective. If your privilege level is encoded in the password, anyone who observes or intercepts your password immediately knows your system access level. Passwords should be cryptographic secrets, not permission maps.
And option B, tying an account to a physical port. That would mean an administrator could only fix the router if they were physically standing in the data center plugged into a specific hole. You'd completely eliminate remote management.
Exactly. It destroys flexibility entirely. Now, option D is a tricky distractor. Secondary authentication, like a Radius server or 2-factor authentication, is highly recommended for security, but it is not how Junos primarily defines the permissions inside the OS itself. The external server just verifies you are who you say you are.
Which leaves us with option C, by assigning the user account to a specific login class.
Right. Junos uses predefined or custom login classes, like superuser, operator, or read-only. When you log in, Junos checks your class, and that class dictates exactly which operational commands and configuration hierarchies you are allowed to even see, let alone modify.
All right, we are stepping down from the high-level management plane into local physical reality. For question 9, what is the primary function of the address resolution protocol in a local area network?
The ARP protocol.
Yes. Option A is to map a logical network address to a physical hardware address. Option B, to assign dynamic Internet Protocol addresses to newly connected devices. Option C, to translate private internal addresses into public external addresses. And Option D, to encrypt data frames before they are transmitted over the physical medium.
Address Resolution Protocol, or ARP. It is basically the glue of the local network. Option B describes DHCP, the protocol that hands out IPs. Option C describes NAT, which handles public-to-private translation at the network border. And option D describes encryption protocols like IPsec or MXSec.
Leaving option A is correct. To map a logical network address to a physical hardware address. But how does that actually work mechanically? I mean, why do we need two addresses?
Because IP addresses are logical and they can change, but devices communicate locally using burned-in physical addresses called MX addresses. If your computer wants to send data to the router on the same local Ethernet switch, it knows the router's IP address. But Ethernet switches don't understand IP addresses. They only route based on MX addresses.
So the computer sends out an ARP request. It's essentially throwing a dinner party.
I like where this is going.
Yeah, the IP address is the guest's name on the formal invitation, but the MSC address is the physical chair they are actually assigned to sit in at the table. ARP is basically the host of the party standing in the room and shouting a broadcast message to everyone. Hey, who has this specific IP address and what is your exact physical MSC address?
And the specific device that owns that IP address replies with a direct unicast message. That's me, and here is my physical MSC address. Now the two devices can encapsulate the data into an Ethernet frame and actually communicate across the physical wire.
It's brilliant. Okay, let's zoom all the way back out to global scale for our final question. Question 10. Which two statements correctly describe the characteristics of Internet Protocol version 6 addressing?
Okay, let's bring it home.
Option A. It eliminates the strict need for network address translation in most environments. Option B. Addresses are represented exclusively in standard decimal format. Option C, it relies on traditional broadcast messages to resolve hardware addresses. And option D, it utilizes a 128-bit address space.
We need two correct statements. We can easily eliminate option B based on our earlier discussion about hexadecimal shortening rules. IPv6 uses hex, not decimal. Option C is also fundamentally incorrect. We just talked about how ARP uses broadcast messages in IPv4, but in IPv6, broadcast radiation is entirely eliminated. IPv6 uses highly targeted multicast messages to resolve hardware addresses, making the network far more efficient.
So A and D must be the correct pair. It eliminates the strict need for NAT, and it utilizes a 128-bit address space. How do those two connect, though?
They are directly causal. Back in IPv4, we only had about 4 billion addresses total. So we invented network address translation, or NAT, to hide thousands of private internal corporate computers behind a single public IP address. It was a band-aid to stop the internet from running out of space. But IPv6 uses a 128-bit address space.
And the sheer math of a 128-bit space is staggering. I mean, it's enough to give every single grain of sand on planet Earth its own public IP address, because the space is virtually infinite. We don't need the NAT band-aid anymore. Every device, from a server to a smart light bulb, can have its own direct public address for true end-to-end global communication. Thank you all for watching. See you in the next video.